Okay, welcome back. Our next speaker is Neil Mitchell from Barclays, and he's going to talk about fast XML parsing in Haskell. Thank you.
Thank you very much, Andres. Slides. One second, just waiting for the slides to show up. They're on my screen. So in this talk, I'm going to talk about fast XML parsing. And I'm just going to go straight into optimization, making Haskell fast, interfacing with C libraries, all these things. But that doesn't mean I didn't do all these things that you should always do before doing optimization. I profiled, I benchmarked, I did all this dull stuff which doesn't make for a good talk. So I'm not saying copy me, I'm saying do this as well. So just my disclaimer. So on with fast XML parsing. So about a year ago, I had a problem. I was doing a lot of XML parsing, and it was taking a significant amount of the time in my program. So, all right, find a faster XML parser. Looked around all the Haskell XML parsing libraries, and they weren't very fast. So I wrote my own, and I did it by interfacing to C, by writing it basically in C, and then interfacing to it with the FFI. Put it up on my blog post, used it a bit, and then Christopher Dunn emailed me and said, I don't like doing things in C and Haskell. You should just write fast code in Haskell. Do you mind if I take your work and basically publicly trash it by showing how much better you can do in pure Haskell? And I said, I'd be delighted. So he wrote a blog post, and then I replied to him saying, do you mind if I take your work and present it at the Haskell Exchange? And he said, no, I'd be delighted. So all bugs are my fault, but this is very much a joint effort with Christopher Dunn, who hasn't seen the slides and has no comment on them thus far. So before I start, I'd kind of like to revisit an optimization folklore that you often hear banded around. So 90% of the code of the time in a program is spent in 100 lines of the code. So that's slightly true, but my experience actually is not as true as it is for undergraduate projects, whereas in real systems it's not quite that simple. So generally, most real systems, they take in a bunch of data, give it some structure, do a clever algorithm, and then output it. So this very much parse, process, output pipeline. And depending on which part of the stage you're optimizing, depends on what techniques you should be using. So something like parsing is typically about fast in a loop. So it's an ON algorithm. You have to visit every character, and you want to do it with as few machine instructions as possible. Something in the process space is usually more like, oh, I'll pick a smart algorithm, good data structures, cache locality, ON, log n algorithms. And then in the output space, it's about input-output speed. So it's interleaving, buying an SSD disk. And also, after you've optimized your code, your profile will probably be flat. So while it's true that 100 lines takes all the time in the beginning, by the time you've optimized, that's no longer true. So bearing in mind this, I'm going to focus on this very much parsing and fast in the loops from my Haskell program. So let's look at the problem concretely. Imagine I have an XML document. I'm guessing everyone here has seen XML documents before. It would be almost impressive if you hadn't. So let's imagine this XML document here, which only recently underwent minor revisions. And the idea is we want to do a DOM, to produce a DOM tree. So the idea is we can get pass in this big string and produce a memory object from which we can say, well, what are the root nodes? Given a node, what are its child nodes? So given the conference node, what talks does it have? Find me all the talks nodes. Find me all the authors. Those kind of queries. So it's very much translate it to an in-memory, kind of hash maps, that kind of thing, and peek around in it. And we want to do this fast. So I looked on kind of around Hackage, and I found lots of solutions for XML parsing. So when you see lots of things and you're looking for something fast and production quality, I did my usual trick of find out which one Michael Snoyman uses. And the answer is XML conduit. And so I asked him, oh, how fast is this? Have you benchmarked it? And he's like, no, actually, I've never benchmarked it. I use it all the time, but it never occurred to me to benchmark it. It's a bit unusual. So I started benchmarking them, and they were laughable slow. So compared to the solution we come up with to the end of this talk, we're talking like 100, 300, so much slower I couldn't be bothered, not really a DOM-based parser. Yeah, they're all awful. But the one that, awful performance-wise, which was never their focus. So, I mean, maybe it's unfair to say awful. But the one which kind of caught my eye was XML. So XML is a C++ library, and it's known for being the fastest XML parser. There are chapters in books written about how it is the fastest XML parser. So I saw a XML binding for Haskell, and I thought, great, this will be the one to use. Unfortunately, it kind of segfaults a lot. Its memory management doesn't match the semantics of XML, so just segfaults, which is not very good. It's also a C++ library. And while Haskell is excellent at wrapping C++ libraries, it's very hard to distribute a wrapped C++ library because you require extra runtime DLLs. So all the users of your library have to do some fancy setup magic, which is pretty horrible. Whereas a plain C library, much easier, just compile straight in, nothing interesting to do. So I'm going to write my own XML library. Maybe that was a step too far already, and I should just improve the Pudgy bindings, but that's where I got to. So let's think about what tricks does Pudgy XML do to be as fast as it is. So when I say it's fast, it really is fast. And they've benchmarked against all the libraries, which I didn't bother doing for this talk. But they're 9 times faster than libxml, 27 times faster than the Microsoft one. The only ones that are even in the same ballpark are ASM XML, which only works on an x86 32-bit CPU, and Rapid XML, which is a little bit slower, but still in the same ballpark. And so fast, they wrote a chapter in a book, The Performance of Open Source Software, that has Parsing XML at the speed of light. It's quite a good book. It also includes a chapter on warp, if you're more into the Haskell side. So what did they do to be fast? Well, firstly, they ignored all the doc type specification because no one understands what it means and no one uses it. They don't bother validating, so XML documents can have a validation schema, lots of complex rules there. Again, no one really uses them. And they do in-place parsing. So essentially, given the string, instead of allocating fresh buffers for each piece, so they take in this whole string, and rather than allocating a buffer to represent Neil Mitchell, they just point at the string they took in. So this is really handy. It's a very important trick if you want to avoid allocations, avoid memory copies, and get high-performance XML parsing. OK, so those are good tricks, but we want to go even faster, so we're going to throw in some of our own tricks. So ignore the doc type, don't validate, but we're going to do even more in-place parsing. So XML documents have escape characters in them. So you'll see things like ampersand LT semicolon, and this stands for less than character. And ampersand AMP semicolon stands for the ampersand character. So when you encounter one of those, you need to start shifting your buffer to replace the ampersand with replace that lump with an actual less than symbol. That's too slow, so we don't bother. We just leave them unescaped in the document, and if you want to unwrap those escaping characters, you can do it yourself later. But that means all our strings are literal offsets into the source of an unmodified document, whereas Pudgy XML has to mutate the string it gets in. And when we're in the body text, the only interesting character to us is the less than character, so we can just defer everything to memchur, the fast C implementation that has SIMD, buffer aligned, all the clever stuff that goes into a C compiler or a C runtime library, we can just defer to it. Taking these ideas, we developed 2 libraries. Well, so I developed XML, which you can basically think of as a C library for XML parsing, combined with a Haskell FFI onto it, but the C library was designed to make the Haskell FFI easy. And then Christopher came over and did Zeno, which is pure Haskell, but using the same ideas, a bit more friendly. So this is kind of a natural experiment. Two reasonably experienced software developers faced the same problem with similar backgrounds in different languages. So we can actually compare and contrast, kind of that natural experiment that academic papers keep trying to do with programming language comparisons. And it's very hard to do, but we managed it for once. So let's see how we do. So if we're thinking about the difference between C and Haskell for doing inner loops, what kind of things might we expect to be relevant here? Well, so the first kind of concern when you're doing inner loops is security. So if you're using C program, there's an inner loop in C, you're probably dereferencing into an arbitrary buffer a lot of times, and it's hilariously unsafe. But even if you're doing inner loops in Haskell, often people will omit the bounds checks and then not use liquid Haskell to prove they're safe. So there's still a security aspect. Do you pay for the bounds checks? Do you not pay for the bounds checks? Do you statically eliminate them? So it's a concern. In Haskell programs, we're very used to freely and flexibly allocating memory. So in a world like Java, you always write the new keyword before allocating memory, and it's a big thing to allocate memory. In Haskell, we're so used to allocating memory, we just allocate it like it's going out of season. But that's terrible for performance. Whereas in a language like C, it's incredibly difficult to allocate memory, so you're never going to do it by accident. And if we look at the kind of other differences, in Haskell, we kind of write beautiful code, and then we fight with the compiler to optimize it. Whereas in C, we write ugly code, and the compiler does a very good job of optimizing it. So it's a very different approach, and I'm going to try and give you a flavor. This isn't meant to be a tutorial on doing either, but kind of a flavor of the experience you'll go through if you do these two things. And the list of C disadvantages kind of trails off the page with seg faults, undefined behavior, portability. And I suffered through all of these, so they're all real. So first, I'm going to talk about the XML library. And I'm going to show quite a lot of code. I'm going to go quite a lot into the detail and the flavor. So please do jump in with any questions you have at any point. I've got 2 hours of material, so we're not going to cover it all. So get the most out of what you see. So, who here knows C? OK, good. I think every Haskell programmer should also learn C because they provide a nice complement, and you have a much better understanding of what's really going on. And it's also great for doing the fast stuff if you need to. So in C, basically, you spend all your time thinking about where memory is, who owns it, who allocated it, and who will free it. So if we take the problem of XML parsing, where does our memory end up? So essentially, you start with a big string. And this is the text of the XML document you're going to parse. And in our code, we're going to use a Haskell byte string. So the string lives on the Haskell heap and is encapsulated in a byte string. And we're going to pick a byte string because the byte string, secretly, is just a pointer to a block of memory that is accessible by C, and all the operations happen in C in byte string anyway. So that's nice and easy. And the other concepts we kind of need to model are the document, so the whole XML document, a node, many nodes in the document, and attributes. So attributes can live on nodes, nodes can live inside other nodes, and nodes can live in the document. But rather than try and model that complex hierarchy in C, we're just going to simplify things. And inside the document object, we're going to have a big block allocator. So anything that needs a document or an attribute will be able to ask, a node or an attribute will be able to ask the document, allocate one of these for me. And then the document itself retains all the memory, does all the life cycling. So essentially, there is a big document in C with some mallocs, and we can free that as a whole. we can track it as a whole, and we can lifecycle it well. So the node and the attribute are just pointers into the document. And then all of it, the document, the nodes, and the attributes, point into the Haskell byte string. That makes some kind of sense? So to get the interface to Haskell, we need to start thinking about what the interface looks like at the C level. So first, we're going to define a struct called str, which is just an int32 start and length position. So this is essentially a substring construction onto our big byte string in the Haskell world. And you'll notice we haven't mentioned which byte string we're allocating into. So if you look at the Haskell byte string, it consists of three things: a pointer, a start, and an end. We don't need the pointer because there's only one byte string in our world, so we'll just assume it's implicit. And we'll pass it round as an extra argument. And then if we look at something like a node in our world, a document node, what kind of strings are we interested in? So the three strings that are most interesting for a node are, if you kind of imagine the node, you could see the foo, so this first one, the name of the string, and you can see this is just the bit between the opening angle brackets. There's the inner text, the body of the node, and again, just the bit between the opening and closing. And there's the whole thing, which is the beginning of the tag to the end of the tag. So we can start building up data types that represent the thing we're interested in modeling. And then we can build some functions that operate on these things. Again, this is all in the C world, and we'll show how to wrap it into Haskell later. So starting at the top, we've got a document parse function. So this takes a C string. So C strings don't have a length. They have no concept of length. So we pass in the pointer to the first character and the length separately, and we get out a document. Given a document, we can see, was it an error? Given a document, we can get the node that represents it, and we can free it. So we've got ways of manipulating our document object, and then we've also got ways of manipulating and kind of introspecting our nodes. So for example, node attributes, given a document and a node, I can get the list of attributes that it contains. But because this is C, I can't just return a list of attributes. I instead return a pointer to the first attribute, and the final argument I pass in is a pointer to an integer that gets written the length of the array. So you can see that things like where in Haskell this would be list of attra, I've encoded it as pointers to buffers that get mutated with lengths and unsafe pointers to other things that I arbitrarily index in the future. So a lot of complexity and a lot of explicitness. Even if I was doing this for C, I might have done it in a better way. But because I'm doing it in Haskell, I'm trying to be very explicit in all the steps. And then for things like node attribute, which is essentially a search function, I also return an attra star, a pointer to an attribute. But this time, it's really a maybe attribute, and null means nothing. So I'm using the same kind of types to represent very different things. So how did I come up with that? The sad answer is I kind of thought very hard, used experience of writing FFI, and then wrote down what I thought was the right answer. But if I kind of try and really think, what was I doing? So it's simple. It's explicit. All the memory is handled nicely. The functions are relatively big. There isn't a function to parse a little bit and then get some more characters. It's a big parse everything at once. And I use byte string because it's FFI friendly, because I know it's a C pointer underneath. And it's all about intuition and experience, unfortunately. So I've got my simple C model. I want to reflect that into Haskell. So I want to build a nice, friendly Haskell binding that wraps away all this complexity, all this high-performance C, which, trust me, I wrote, but you can check the repo for that. So when I see things like this struct which is basically a pair of ints, I can reflect that into Haskell very directly by declaring a data type str that is a pair of ints. And you'll notice I've used int32s in both places, so they line up perfectly. one of the problems of using C and Haskell is that you have to match the boundaries perfectly, so it's quite nice to be explicit. And we can just write storable instances. And a storable instance is essentially, given a block of memory, how do I put the str into it, and how do I get the str out of it? So it's all grim, I/O, pointer poking code. And if you write any of these numbers wrong, your program will segfault. So you have to be very careful. Wrapping Haskell functions into C functions into Haskell, in contrast, is way easier. You basically take the C function and write it down with a Haskell signature instead. So where I'm using pointers to nodes and pointers to documents, I fake up a new type just to serve as a phantom type index on the pointer, so I can track what's a pointer to a document and what's a pointer to a node. And then I just write foreign import, call, name of the function, and then transliterate all the arguments. Very simple. The kind of complicated bits are that I put everything in I/O because these are all C functions. They all go read and mutate memory highly unsafely. So they need to be in I/O, so I get the ordering of allocation, exploration, all that right. For the free thing, I've made it a fun pointer rather than a normal thing. So the idea is I'm not getting a Haskell function to free the document. I'm getting a pointer to the C function to free the document. We'll see why that matters in a bit. And I shove the word unsafe in because it makes things go faster for some things. The exact semantics of unsafe seem to be known only to Simon Marlowe precisely. But essentially, you're saying, by writing unsafe document node, I'm saying this function is super safe, which really confuses me. But I think it's safe with respect to the FFI. It's safe with respect to something, but it's not the thing you expect. Anyway, just write it without the unsafe, and someone will come along with a pull request to make all the suitable things unsafe later. That's what happened for XML. So where it gets harder is wrapping the memory that lives in the C side. So in the C side, I have an explicit document object. But actually, the only thing a document provides is a node. So I'm going to conflate the two things on the Haskell side for a simpler interface. But what must a node or a document know? And it's essentially the string that we started with, so that when we're doing the indexing, we can produce nice byte strings indexed into that string. It must know the document it's working with, so it's got the indexes into all the buffers and the nodes and everything. And it must have the node you're actually working with, which will change as we explore the document. So the one thing we've changed here is foreign putter. So this essentially says, I have a pointer to a C node. A foreign putter says I have a pointer into C world, and I have a way to free the C memory once it's no longer being used. So sometime after the very last time I touched this lump, the document will be freed automatically. So I've now kind of built garbage collection on top of manual memory management. So how do I create that node? Well, so I can parse it, and basically I can unpack the byte string as a C string. I can document parse. I can create the foreign pointer for document free, and I can produce the node from it. So I can build these things up. And I guess the interesting thing here is not really these details, but this unsafe perform IO at the top. What I've done is I've taken my lots of impure, unsafe C functions, which have manual memory management, and all the details that I really don't want a Haskell programmer to see, and I've hidden them. So the function itself just takes a byte string and returns a node, and the unsafe perform IO is saying, don't worry, I personally have checked that all of these impure operations, once you group them in this way and have this kind of lens on the world with all these other functions, they're safe. The impurity doesn't leak. So this is why it's very difficult to choose exactly the right primitives to build up the pure abstraction afterwards. I can do the same kind of thing with the accessor functions. So I showed you before we were returning pointers and allocated memory and all this gunk. Now my attributes function is just a node to a list of attributes. And under the hood, I do some unspeakably horrible things with unwrapping foreign pointers, allocating memory on the stack, doing peeks and pokes. It's all grim. But rather than dwell on those details, it's just the idea that I've taken complexity and hidden it. So very much the big picture is write simple functions in C with simple types, wrap them into Haskell almost mechanically, and then define some types that represent them in some sense, and then finally turn those pieces of gunk, which feel like coding in C, into something that feels like coding in Haskell. So there's do C like C, do Haskell like C, do Haskell like Haskell. And it's the final step that's hard. So I hope that gives a kind of flavor of how you might go about it. The details, they're all in the repo if you need them, but that's the kind of approach we're going to take. So note that I haven't actually shown any of the C code. That you have to write yourself. So once we've got this nice Haskell interface, we do everything we would do anyway. So we do the testing in Haskell, we write quick check properties, we write examples. So for example, we check that if you take an XML document, render it to a string, and then parse it, you should get the same thing you came in with. So lots of nice testing. And I will say that debugging C, I forgot how painful it was. Printf debugging is not enough. So I use Visual Studio for interactive debugging and American Fuzzy Lop for kind of fuzz testing and seg fault checking. And thanks to Austin Seep, who explained to me how to do all that. But at the end of it, we get something quite nice. So we get XML, which is about 2 times faster than Pooji XML. It's simple. It's got a nice, clean interface. You can abstract things on top of it with, there's like the XML lens library, which gives you lenses on top of this. And that library didn't need to know I was working in C. We've kind of hidden that very nicely. But of course, it was a horrible experience writing C, because there was undefined behavior, buffer overruns, blah, 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 blah. So then Christopher emails me and says, we can do it much better with pure Haskell. And I guess the nice thing about this is that the approach I took with XML was basically think really hard and consider all the details and then make sure every line of code was perfect. Whereas with Zeno, which is the library Christopher implemented, there's a much more explainable methodology about how you might go and approach writing a fast parser. So we're going to follow this and see how we do. So Christopher's approach was basically watch memory like a hawk, start simple and benchmark, make changes and benchmark, and build up composable pieces. So very much start small and build up. So what's the simplest thing we can do that is a bit like parsing an XML document? So yeah, look for the beginning and end angle brackets was said. So let's do that. So we can, given a string and an index into it, we can look for an opening angle bracket, look for a closing angle bracket, and then continue on throwing away the result of what we just found. But we've walked the document looking for angle brackets. And we can write a little helper function that essentially, given a character and a byte string, finds the next character. So let's see how fast that is compared to XML. Oh, it's actually about 2 to 3 times faster than XML. That's a nice result. So is that a surprising result? Well, kind of not really. Essentially, the byte string is all implemented in C anyway. So we're basically benchmarking the C memchur function against the C memchur function in XML, plus a bunch of allocation and extra work. So we can get our tightest inner loop, which does nothing, just as fast as XML. And not only that, but in our example in that code, that actually includes bounds checking, which actually Zeno includes bounds checking throughout. Perhaps we could remove it with Haskell and go even faster. But it does show that Haskell itself isn't adding huge overhead, which is nice to see. So the other thing we can measure is how much memory this little simple loop is allocating. And if you use the way package on Haskell, the answer is basically for a 4 kilobyte document, it allocates about a kilobyte. For a 128 kilobyte document, allocates about a kilobyte. So basically, it's not using it's not linear order allocation to parse this document. So is that what we expected? Well, kind of if you look at the code, you'll see a just for each opening and closing angle bracket. So this just here. Didn't we allocate that? What happened to it? Any ideas? Well, it returns unit, but to return the unit, even though it's returning unit, GHC didn't just optimize the whole program away to a return unit. It actually walked the entire document to do it. And it went through finding the next character and pattern matching on this just.
But so it creates the constructor that immediately analyzes it, so it doesn't have to.
So the hypothesis was it creates the constructor and then immediately analyze it so it doesn't have to allocate it? Approximately. Effectively, it doesn't allocate the constructor at all. Because if you look at the bs_lm_index function, which really is a mapper over mapture, this does a test, allocates nothing or a just, but it's inlineable. And so is findNext, which builds maybe a nothing or a just on top of that. And so it all kind of gets smushed into the parse tags. And effectively, instead of allocating the just, it immediately puts the code that would have done the just here. So it gets rid of the just entirely. So is just really that expensive? Well, no, not really. In fact, allocation in Haskell is incredibly fast. People coming from other languages often think, oh, allocation, that must be slow. It's like, no. Allocation is maybe a few machine instructions. But what adds up is, well, if you're going to do allocation, you need to heap check the function before you start. So check there's enough heap that if you did the allocation, you wouldn't have a problem. You need to do the allocation, which is basically an integer addition on a CPU register, so basically free. You need to do the construction of the object, which is poke the relevant pieces into the block of memory you've allocated. You need to do the examination of that thing, so read the memory, and then do a jump based on what it says. That's relatively expensive. And then every so often you need to do a garbage collection because you're allocating a lot of stuff. So none of these are expensive. It's just not free. And if you're competing with doing really high performance stuff, it really does need to be free. So now we've got this simple structure, we can incrementally add bits. We can add parsing comments, add tags, attributes, all that kind of stuff. And then we can start returning some results. And at each step, we need to benchmark and check the memory hasn't increased. And it will at some points, and you'll need to do profiling, inline pragmas, extra optimization levels, all these things. But you can approach the problem one small slice at a time. And then finally, to actually make it useful, you need to start returning something more than a unit. So you can follow the traditional fold pattern and essentially pass in functions for each of the constructors you would like. So when we pass in an f tag, which is what we'd like to use to build our tag. And then here, we pass tags and pass f tags. And we call f tag with the string we've got. So essentially, it's call functions that make the stuff useful. Okay, and in the end, you end up with something like this. So functions for all the different types of things you might see, and a byte string in. And the really nice thing here is, whereas with XML, we kind of built a DOM in one go, now we really have a streaming incremental parser from which we can build a DOM, or which we can use it directly. And this is really powerful. We've got a much greater level of abstraction in the Haskell. And how does it work out in the end? Well, the SAX parser, so the streaming one, tends to be a little bit faster than the XML, whereas the constructing the DOM, constructing the whole object, is a bit slower than the XML. But we're in the ballpark, so that's not too bad. XML is still faster, but maybe maybe you don't. Maybe you'd prefer to avoid the C if you can. So we kind of thought there were two approaches to inner loops. So we could go with Haskell or we could go with C. And I've kind of greened and red the things that really turned out to be a problem or turned out to be an advantage. So the Haskell one is much safer because it's not doing random bounds reads. We're using abstractions, but unfortunately we had to play with the compiler, with the inline and the optimization settings. We've tuned it very much for a specific GHC version. This isn't Haskell code. This is GHC 8.2 code, and who knows what GHC 8.4 will do to it. So we're having to make that ongoing compromise in maintenance. Whereas the C, it's going to work in every compiler forevermore with the same performance characteristics. That's nice and safe. The problem we had is we don't have abstractions, it's verbose, it's got undefined behavior, and the security, it's a bit of a security nightmare. Obviously, we can fix these things, but it's painful to get there for the C. I would almost say the C has higher upfront costs, whereas the Haskell maybe has higher ongoing costs. So yeah, in C, it's all about upfront design, whereas in Haskell, it's all about continued vigilance and feedback loops. The Haskell is definitely better at abstraction and security. I will say C is a lot harder than I remember. I thought I knew C, but having written some C, maybe I don't. And the Haskell FFI is exceptionally good. It's very good at, you can get the most out of the code you're calling. It's the best of any language I've seen. And I personally still prefer C in loops to Haskell, but certainly other people differ. OK, thank you very much. Any questions?
One. OK. So you said you use memchr to parse XML. Then how do you handle CData? Do you handle CData?
Well, so CData starts with, so essentially when I'm in a block of text, I look for the angle bracket to finish that. And CData also starts with an angle bracket. CData is introduced, angle bracket.
Right, but there can be unescaped angle brackets inside CData.
Oh, inside, when I'm inside the CData, I have to do something different.
So you track CData?
Yeah. Okay. So currently it doesn't support CData, but there's no reason it shouldn't if I could be bothered to add CData support. But you wouldn't be able to use a memchr inside a CData. You'd have to do something slightly cleverer.
Hi Neil, did you experiment with memory mapped I/O at all? Especially, it seems tempting to me because GHC supports it.
So essentially, from a memory mapped I/O handle, you can produce a byte string. So this works because it takes a byte string in. So I didn't experiment with memory mapped I/O. It wasn't particularly, it wouldn't have worked for the problem I had. But there's no reason you couldn't use the same approach for memory mapped I/O. And in fact, even this literal code.
So you mentioned that the Xeno library is basically building up these functions as a streaming computation rather than like parsing to an intermediate data structure and then having some sort of interpreter for it.
Yeah.
Could you talk about like the performance implications of doing both and the abstractions of doing both? Like I've seen some parsers do both, and I want better clarity on that.
So essentially, if the C did intermediate steps, you would lose everything with the FFI overhead. Whereas for Xeno, it can do stuff with the streaming code, but essentially GHC rips out all the intermediate stuff and directly builds the tree, but the compiler generates the code that does it. So there's no performance impact in the Xeno case of having both available, but they benchmarked really hard and added all the right inline and specialized parameters to make sure that was the case. So if you're careful, you can do both. So since there's a few minutes left, I was going to go through all the things I screwed up, which I think is the fun bit. So when I say C is hard, I really mean it. This is one example of how I screwed up C. But yes.
I was just curious, like you said your C library was 2x fast, or like the thing was 2x faster, and I was curious if that was benchmarked without the alt tags, like where did the speed up come from? Was it like the mutable things that the PG XML library was doing that you weren't?
Yeah, so PGXML spends slightly more time parsing because it's dealing with the escape characters, which we're not bothering with. It also tries to build a quickly searchable DOM. So it spends more time building the document to make searches logarithmically, computationally faster. So it's got hash maps, fast lookups, that kind of thing. We don't do any of that. We just store it as a list on the basis these lists are actually quite short. And you can spend a long time building them, but it's faster just to scan them linearly. For most things, of course, there are certain cases where you'll get an exponential slow down, and it'll be horrible. But you'll find most of the time. So 2 more minutes. So I'll go through some of the things I screwed up, which is quite a lot, actually. And most of these, the screw-ups result in a seg fault, so it's not very nice. So one of the things, characters in C are signed on some platforms. So this code, so the green bold bit is the change I made. This code was indexing 127 characters before the array rather than into the array on some platforms. Buffers are hard, manual memory management is hard, and mutation is hard. So in C, I was accidentally doing basically a get is a peek, look at the character, and a skip, increment the buffer. I did them at the wrong point, and that goes horribly wrong. Mutation doesn't really work. If you miss things to work with foreign pointers in Haskell, you'll segfault, you'll lose the memory. Again, this one I quite liked. So this one took me 3 days. It works in Visual Studio, but not in GCC. And essentially, this is undefined behavior, and segfault's one way round, doesn't the other way around. So this is the kind of things you get to experience with C, and they're multi-day debugging experiences. So you may want to choose the Haskell route if you want, if you can. All right, thank you very much.